In this video, we're going to talk about an example of a group that is not abelian, unlike Z mod 5, which we talked about in the previous video. Suppose I draw a square. So let's assume that this is exactly a square. My drawing skills are not the best, but I think that's at least a decent facsimile of a square there. Okay, so let's say that this is a square. All the sides are congruent, all the angles are right angles. Let's talk about all of the symmetries of the square. Now, the way that we use the word symmetry in this course is a little bit different from the way, or some of the ways that you might be used to using it. So in grade school, you might have learned that a symmetry is like a line that can be used to divide the figure exactly in half, so that both halves are geometrically congruent. And that is sort of part of the way that we think about symmetry here, but actually the way that we're going to think about symmetry in this setting is a symmetry is a function or transformation of the plane in this case, that maps an object onto itself. So in this case, maps the square onto itself. And that doesn't mean that it has to fix every point. For example, I have a vertex here. I can have a symmetry that moves this vertex to some other vertex of the square, like one of these three. Or it could leave this vertex exactly where it is. But a symmetry is just any transformation of the plane that takes this square and transforms it and leaves me with a square that is in the same position. Okay, so let's think about what symmetries there are of this square. So first of all, I do know that there is a line of symmetry that is a reflection symmetry that reflects the square across this line. I'll call that symmetry H. So H is reflection across a horizontal line. Alright, so that's what we will call capital H. And then there's also a line of symmetry here. So I will call V the reflection that transforms or that reflects the square across this vertical line. So V is reflection across a vertical line. And then I also have a diagonal that cuts through the center of the square. And I can reflect the square across that diagonal, and I still get a square. So I'll let D be the name of this reflection. D will be the reflection across this diagonal. And finally, there is one more line of reflection. It's this other diagonal here. And I will let D prime be the reflection across that diagonal. Diagonal. Okay, so we have two diagonals, D and D prime. All right, but those are not all of the symmetries of the square. Those are all the lines of symmetry, but there are other transformations I can perform that map the square onto itself. So one transformation I can perform is a 90-degree rotation. I'll call that R90. R90 is a counterclockwise 90-degree rotation of the square. I can also rotate by 180 degrees. We'll call that R180. I can also rotate by 270 degrees. I'll call that R270. And finally, there is a transformation which does absolutely nothing. We call that the identity transformation. So there's a transformation that just takes the entire square and leaves everything in place. And I'll call that transformation, let's call that I, because that's going to turn out to be the identity element of the group we're about to define. Okay, so I have how many different symmetries here? I have 1, 2, 3, 4 reflections. I've got 3 rotations. And I have this other one here, which we could think of as a rotation in itself. It's just a rotation that does nothing. It's a rotation through an angle of 0. So in a way, we think of this as being 4 rotations and 4 reflections. So these 8 symmetries together, I claim that they make up a group. So I'm just recording all of those up here. And then I have, what do I have? I have H, V, D, and D prime. And collectively, I'm going to call that set D sub 4. Because once we establish that this actually is a group, we haven't proven that yet, but we will, we're going to call this the dihedral group on a regular fourgon. A regular fourgon, of course, is a square. Okay, but wait, why is this a group, though? It's important that we answer that question. And actually, before we can even start answering that question, we need to first decide what the operation is for this group. So what is that? Well, the operation for this group is function composition, because a transformation is just a bijective function from the plane to itself, and I know that one way I can operate with functions is I can compose them. So I'm going to use function composition as our group operation. So for example, if I want to operate with two of these elements together, let's say R90 and D, then I might write R90 composed with D. And I'm going to use the composition symbol here, this symbol, as our group operation name. Okay, so why is this a group? I have an operation, I have a set. The set is the set of these 8 transformations. Let me just highlight that there. So I'm claiming that this set is a group together with this operation here, composition. Okay, so to verify that, first I need to know that this set is closed under the group operation, so closed under composition. And I know that that's going to be true as long as I have determined all of the different symmetries of the square. Because if I compose any two symmetries of an object, that will give me a symmetry. Now I feel like I'm being a little bit glib there, so let me explain what I mean. So a symmetry is just any transformation which maps the square onto the square. So what happens if I compose two symmetries, or compose two such transformations? Well, if I perform the first one, then I've mapped the square onto the square, maybe in a different order, like maybe it's now this way or something. But I've mapped the square onto itself. And then if I apply another symmetry after that, well, then I'm taking that square and I'm mapping it onto the square again. Again, maybe in a different order, but I'm still mapping the square onto itself. So the composition of any two symmetries will take the square and ultimately map that square onto itself in some way. So if I have all of the symmetries of a square here, and I can actually verify that I do, then the composition of any two symmetries should be one of the symmetries in this set, because this has to be some symmetry, and I believe I've listed them all here. And I can actually verify that these two do create one of the symmetries in this set. We might take that up in just a minute. All right, so that's why I know I have closure. Okay, what about associativity? In the last video, we talked about how verifying associativity one case by one is kind of a pain, usually not what we want to do. And in this case, there's a much better way to know that our operation is associative. It's because our operation is actually really just function composition, and function composition is always associative. Okay, what about an identity? Do we have an identity element? Well, the one that looks most promising is this one here. It's the transformation which does nothing to the square. But the fact that this does nothing to the square isn't what makes it the identity. What makes it identity is that I can compose that with any other transformation in the set and get the same thing. So let's check that. So let's suppose x is a symmetry of the square, where x is one of those 8 elements up there. Well, what happens if I compose I with x? Well, that means perform x and then do nothing else, because performing I means really doing nothing. So if I perform x and then do nothing, that's the same as if I just performed x. And similarly, if I compose x with I in that order, then that means, keep in mind, when I write down a composition, I do the one on the right first. So this means I do nothing, and then I perform x. Well, that's the same as if I just performed x. So that means that I is an identity. Yes. Okay, so we have 3 properties, and the 4th property, you'll recall, is that I need each element to have an inverse. So let's verify that. Okay, well, first of all, I know that I composed with itself will be I, so I has an inverse. What about R90? I think that if I compose R90 with R270, then I'm rotating clockwise by 90 degrees. I'm rotating by 270 degrees counterclockwise. Remember, this one goes first, and then by 90 degrees more. So I'm rotating by a total of 360 degrees. That's the same as if I did nothing at all. And I could also compose them in the other order, and I would get the same result. Oh, sorry, that should be a composition there. So that means that R90 and R270 are each other's inverses. R180 composes with itself to give the identity. So R180 is its own inverse. And as a matter of fact, all of the reflections, H, V, D, and D prime, each of those composes with itself to give the identity because, well, what happens if I perform a reflection and then perform the same reflection again? Then I get back to the position I started in. So each of those is its own inverse. So I think I can verify just by one checking that each element has its own inverse. Sometimes the inverse is itself, sometimes it's something else. What about commutativity, though? Do I have commutativity? I don't need that to have a group. Just based on these four properties, I'm already in group land. Okay, so now I'm perfectly fair in calling D4 a dihedral group rather than a dihedral something else. But what about commutativity? Well, let's check out what R90 composed with D would be, and let's compare that with D composed with R90. See if we get the same results. Because I think that those are going to be different enough to where if I compose those in different orders, I might get different results. So check it out. If I have a square here, I'm just going to draw a little miniature and then label vertices to help me keep track. So 1, 2, 3, 4. If I compose, or if I perform D first, I'm reflecting across this line here. So what I get next is a square that's labeled like this. I still have 1 and 3 in place, but 4 and 2 switch. So that's if I perform D. And then if I perform R90 on the result, I'm just rotating everything 90 degrees clockwise. So now I have 1 here, 4 here, 3 here, and 2 here. So that's R90 composed D. Remember, I'm performing D first. What is the actual result of that, by the way? I mean, I've figured out what position the square lands in, but what actual transformation gets me from here to here? I think that is the result of flipping the original square across a vertical line, isn't it? Because I'm switching 1 and 2, and I'm switching 4 and 3. So I can actually say that R90 composed D is the reflection across the vertical. But what about the other way? What if I do decompose R90? Let's try that. So again, I'll draw my little square here. This is starting position. And I can choose starting position to be whatever I want. I can label the vertices however I wish. But then I need to be consistent about how I perform these transformations. R90 gets me to this position. R90 gets me to 1 here, 2 here, 3 here, 4 here. And then reflecting across the diagonal. By the way, notice the diagonal stays in place. The diagonal is always in the same position in the plane. It doesn't move around when I rotate the square. So if I perform D now, what do I have? I believe 4 and 2 will stay put. 3 and 1 will switch. And so now what I have, I think, is the result of taking the original square and reflecting across the horizontal line. So I believe that means that D compose R90 in that order is H. These are not the same result. V is not the same as H. So this means that this function composition, at least for this group, is not commutative. I do not have an abelian group. Okay, but that's all right. Most of the groups we're going to encounter in this course are going to be non-commutative or non-abelian. So we're going to have to get used to working in a setting where we can't count on being able to reorder things.